Get the notes out on chromatography, all right? We're going to do separation techniques in the beginning of this chapter. Today, tomorrow, we have two labs tomorrow because your class. The one is, one's really short, the other one's actually a long one, but it doesn't matter because you'll have a double period and you'll actually be finishing up one of the classes stuff. So I'm going to talk to you about chromatography, which is one of the separation techniques today. Hold on. Hello? Yeah. Yeah. Okay. Bye. You, guidance. You need it.
Do you ever just pray when the phone rings that it's going to be your name to get out of class? I do.
Yeah, except what if you're in trouble?
Well, I mean, you're still out of class.
Yeah.
You can handle a good yelling every once in a while. But
You have to watch the video.
Go. They're waiting for you. All right. So we'll talk about chromatography today, and we'll do two labs on it tomorrow. Then we'll talk about another kind of separation technique called extraction or separatory. We're using a separatory funnel. We'll do that on Monday and Tuesday. Wednesday, obviously, we have half a day, so we're probably just going to watch a video. I have a good Thanksgiving video to watch. That will end our separation stuff. Then we're going to talk about mechanisms the rest of the time, and we have one last little day on some simple common naming things. All right, let's start with the chromatography, though. I have a little video to start us off. Actually, I need Lizzie. You want to sit over there because you have to work the lights today several times.
What happens to my footrest?
You'll survive.
Put the chair from the door.
All right, I'm going to start off with a little clip here. All these are very short clips, no more than like a minute or two, and they're going to illustrate different points. We'll start off with chromatography, and the clip is from CSI. You've probably seen CSI Miami, CSI New York, all different CSI programs. This one's from CSI. You'll probably recognize the actors and actresses in it. Watch what she's doing in the lab. And thank God Bulkley's not here because the name of the company that made this video is showing that their equipment is being used to do this. The name of the company, unfortunately, is, well, you'll see, and you'll probably know why we're glad Bulkley's at the office. Shh. Yeah, it's an Analtech. Although we all know what we'll do. Now watch what she does. Cuts this off. Watch. We're going to be doing something very similar. We'll be doing that too. That's a pipette. Capillary tube. We'll be using that. And then we'll be doing this.
There were two different inks on the work order, which means the date on the work order was compromised. Tom Harper made a service call to Bianca's house, not in December, but 10 months earlier in February.
Okay, turn that light on. All right, so that's what you use.
Wait, was that sorry?
Yeah, that's right. That's what we're going to use, almost exactly what we're going to do. What did she do there? Can you figure it out? She cut up that date into different parts and took samples of the ink. She dissolved the ink, took samples of it, with it, and sucked it up with a little capillary tube. We've seen capillary tubes before. You're going to use them again tomorrow. It sucks up small amounts of stuff. Touched it to a paper, a filter paper, that big filter paper, a square filter paper, and then the different inks in different places, and she ran it and found out that parts of the date were not the same ink because they separated out differently than the other parts of the ink. And that's exactly what you guys are going to do. You're going to use food coloring. You're going to use markers and possibly one other thing we're going to check. All right, but that's what chromatography is. You simply have a piece of filter paper and a liquid, and it basically let the liquid climb the filter paper. It does that by capillary action, basically, because it's attracted to the. You've all seen that. If I put a towel, for example, in water, it's going to suck up the water, like a sponge does. And as that travels, it's going to. If there's more than one color in there, that's why, by the way, it's called chromatography. Chrome meaning color. All right, it's going to separate out into 2 different or 3 different or however many different colors are in there. All right, so let's do that. Let's put notes on this and explain it. All right, all this stuff is going to fit on this first page here. We're not going to finish all the notes today. Not that we wouldn't have enough time, we probably would. But tomorrow in the lab, it's a very short lab, and I'll talk about column chromatography then. All right, what is chromatography? All right, well, basically, in a chromatography, every chromatography, you have 2 major things, a stationary phase and a mobile phase. Okay? And a substance is passed through the stationary phase by means of a moving, either liquid or gas, mobile phase. Here he comes.
Broccoli's coming back.
Yeah, you get to move.
This is a hassle.
I'm going to give you that short. All right. So it's in the case of chromatography, the stationary phase is just filter paper, and the mobile phase is some liquid, usually a different combination of chemicals that have a varying polarity, depending on what you want to separate. All right. Now we can identify and separate these guys based on how far they move or how fast they move up that paper. See, some of the colors are going to be attracted more to the paper than to the liquid moving through it. Others will be attracted more to the liquid than to the paper. The ones that are attracted more to the liquid, they're going to go further. And the ones that are attracted more to the paper, they're going to stay kind of where they were. Okay? So the substance will be separated and identified by how fast or how far it moves along the stationary phase. This lab was very successful last period. You guys will like it tomorrow. It's a very easy lab to do, and it gives you very dramatic results when we do chromatography. So again, what determines how far or how fast it moves? The attraction to the 2 different phases, the stationary or the mobile. Substances with great attraction for the stationary phase, they're going to take longer to pass through, or they're just not going to move as far, depending on which kind of chromatography we're talking about. Things that have greater attraction to the mobile phase, they're going to move further. Now, what would determine, that's what I want you to think about next. I'm going to list several things that would determine whether somebody's attracted to water, for example, versus a non-polar or like an organic substance. Like, what would determine that? What do we know? What determines solubility? What's the one rule of solubility? Remember it? Like dissolves like. And that's talking about polarity, charged. Okay, so polarity is a big deal. Turns out in the paper chromatography and in the column chromatography, the stationary phase is rather non-polar. And the liquid that's going to be moving up, we're going to be doing in those labs, is a variation of polarities. Depending on, like for example, when we do the column chromatography, we're going to have 5% alcohol solution, 25%, and 70%. So depending on how polar or non-polar it is, it will be attracted to that phase. Besides polarity, besides solubility in the solution, what else would determine how far or how fast those guys moved up that paper? Something very, very basic. Something that if I asked a kid in elementary school would probably say, why would one move faster or farther, would say this answer. It's not a chemistry thing. Think. Why would things move faster? Why do things move faster or farther? Somebody?
Weight.
Weight, exactly. How heavy they are. All right? Obviously, if I've got a race and I'm running,
It's Lizzie.
Lizzie versus Mr. Bulkley, not him. I meant his dad. Someone even bigger. Someone maybe like Mr. Norris. Mr. Norris. I have a feeling Lizzie's going to win. It's just going to be, she's lighter. Let's just put it that way. So polarity, the molecular mass, the solubility, and different functional groups will affect how well these guys are attracted to one state phase or the other, and therefore determine the retention time, which would be how long it takes to move through something, or just how far it moves. Now, there actually are calculations involved in chromatography, at least in the first one we're going to do, paper chromatography. We're actually going to be able to do calculations. That's why I've got a picture down below. I'll show you how to do those. But let's talk about them now individually. We'll talk about paper and chromatography, gas chromatography, and column chromatography. The last one, column one, we'll save till tomorrow because that's what we're going to be doing. Okay? Start with paper. Paper chromatography, what you saw in that video clip. And basically, in a paper chromatography, the stationary phase is filter paper, and the mobile phase is some liquid, all right, that's going to be traveling up the filter paper. A lot of this chromatography paper is special, all right. It's made to be very absorbent. Okay. And the sample, as it travels up here, will be dissolved in well, to some extent it will be dissolved in the liquid phase. Now, if I did this, and I tried this, I've done this before, although it's kind of boring. If I have you put a permanent marker, we're going to check different markers out, right? If I have you put a permanent marker on the bottom of that chromatography paper, and the water goes through it, well, the permanent marker is permanent because it's not soluble in water. So what's going to happen to that spot I put at the bottom of the paper? It's not going to go anywhere. It's going to stay there. So it's kind of boring. We don't usually do that when we want to see some results. All right. So the sample's dissolved, if it can be dissolved, in the liquid, and then it travels up the filter paper by capillary action. Remember capillary action?
No.
Okay. And you're going to see a capillary tube. You saw her use one a minute ago in the video clip. You're going to use that tomorrow as well. By the way, in that video clip you saw, the reason somebody made that would be the company that makes all that equipment. Notice as she was doing the different jobs, they had like what equipment she was using.
We should watch it again.
No, maybe at the end.
You'll enjoy it.
Yeah,
Is it on
skills.
YouTube?
No, both ways funny.
It's shown on YouTube?
No, it will be when I finish this up. All right. So look at your paper here. Let me show you how you start it and then what happens. You're going to fill up. It's going to be a plastic tube. As a matter of fact, I should probably get it so I can show you because your thing is going to be tomorrow.
You'll enjoy it.
You'll
think it's absolutely hilarious.
just the name of the company.
Just the name of it. I'm not telling you.
You gotta watch it for yourself.
I mean, everything after the name
It's
of
not,
it.
it's not Language Street.
It's not Wayne.
It's almost as bad though.
No.
Just plastic.
I mean,
Oh, thank you.
I'm just going to.
All right, take a look. You have this plastic tube that has a lid that goes on it. You're going to put in the bottom of that, you're going to just pour in some acetic acid solution, acetic acid and water. Okay, so that's where the water, this says just water. That's where the water level will be at the bottom. Then you put your filter paper, which you cut out of here. Okay, and you got to be careful. This is just a strip of paper, and you'll cut it to the right length. And you'll make a line at the bottom in pencil, not in ink. Why not in ink? Yeah, the ink will run, so you make it in pencil. All right, what will happen is you put that in here, you put the lid on it. Okay, you put the lid on, and you're going to let them sit. Now, it's going to take about an hour to do this. That's why we're going to do this lab first, in our double period. And while we're waiting for this to be done, we'll do the other lab. Okay? You're also going to you're going to have a lot of time in this double period tomorrow. You're going to actually use all of it because you're going to have to finish up the other classes. And we had one period yesterday or tomorrow, right? Well, theirs is going to start in period 1, but it won't be finished till period whatever, somewhere in the middle of period 3 probably. So you'll take theirs out, hang theirs up, and I'll have your own. There'll only be. I'll probably just have to do those my prep period and take those out. Doesn't take that long. All right. As they sit there and they travel, even though it started out as a black dot or a purple dot or whatever, as it travels up, it's going to separate into different colors. All right. Over time, it will separate over the course of the hour you're letting it sit, and you will see when you're all done, different spots. All right. Those spots. I told you there's a calculation to do. I can calculate based on how far this guy moved versus how far the water moved, what's called the RF value. You have to write this down at the bottom, RF value. The RF value is just the ds over df, where ds stands for the distance traveled by the substance, the color, and the df stands for the distance traveled by the solvent front. That's this stuff here.
This is starting to be like physics. I don't like
No,
that.
this is very easy. This is not by any means physics. It's a simple division problem. There's no integration or anything like that. So the distance traveled by a substance is ds. df is the distance traveled by. This is not d as if you usually see a derivative of or something like that. Okay. Very, very simple. You simply get your ruler out. You measure how far the purple spot went, and then you measure how far the whole water went, and you divide it. What's the high? If you do that, what's the highest number you could possibly get? It's going to be the distance traveled by the substance over the distance traveled by the solvent. 1. And that can happen. You can actually get 1 if they travel the same distance. Okay? Label these over here so you know. df is this guy right here. That's how far the water travels. You should have it. I give it to you. Oh, you weren't here yesterday. I'll give it to you. ds and ds 1 and 2. Here you go.
Alright, you can't even see DS2 on.
Well, I was just going to say, you probably can't see the yellow color on here, so you want to make in pencil where your 2 spots are, okay? Because there will be on your paper probably more than 1 color. But some will only separate out into 1 color. So that's pretty easy, right? That's what you'll be doing on Friday. All right, but the lab's going to take a while because you got to actually set it up and do part of the other classes too. So that's paper chromatography. It's really a pretty neat lab. I think you'll like it. Everybody liked the column one too. All right, let's look at gas chromatography. A couple of video clips here. Same thing, a minute or 2 long. These are not quite as.
Is it the same?
No, not the same.
I don't even know what the company is.
You will. You will. Trust me. We'll show it to you later.
No.
All right, gas chromatography.
Stop getting-
Turn the light off, please. Okay. Pay attention. This is the first one, although not great quality, actually is a better description of what's going on in gas chromatography. Here, your mobile phase is not a liquid. It's a gas, as implied by there. And the solid phase is not paper. It's a column, like a tube, wrapped in a coil inside a machine. Now, I actually have had, there's a, Wilkes has a program, Science in Motion, and I think Bloom has a program, where they have a van of professors from university come up with students, and they will do a lab for me. I've done this in the past. Actually, Mrs. Spencer's done it every year when she was teaching biology, AP Bio. She'd have them come up like 2-3 times a year. And they would do labs that I couldn't afford the equipment for. I mean, we're not going to have this piece of equipment they're going to demonstrate here and in the next little video clip. Costs thousands and thousands of dollars. So you can't just buy this for a high school. It'd be silly.
We're not that good.
We're not that rich. Now, Dayton, watch the video clip. Otherwise, you won't have seen this, and you won't know this either. Watch.
It's a method of separating a mixture of compounds which can be vaporized into its various constituents. It consists, quite simply, of a very fine coiled tube, usually made of glass or stainless steel, which has a pure carrier gas flowing through it constantly and at a precisely controlled temperature. Distributed throughout the coil, you have a porous adsorbent. At one end, you inject the liquid mixture of
So you put
compounds.
this in here.
This vaporizes
And it's vaporized by
immediately in the
heat.
heat, and the
Watch.
vapor is carried by the gas through the coil. Since each of the constituents of a mixture has different chemical and physical properties, some will be more slowed down by the adsorbent than others. So they move through the coil at different speeds. So you squirt the mixture in at one end, and by the intensity of the signal given off by each compound at the other end, you can read off the different constituents.
Now, like I said, the quality of that one's poor, the next one's better, but that's actually a better description, that's why I put this one in here, of what's going on inside the machine. This one's going to be much better quality, you can see things better, but it doesn't really show you what's going on. That coil, okay, you're pushing with gas, usually helium gas, you're pushing this mixture through there, and as you saw, did you see any of those poor quality, how some are going to go, some of those components of the mixture are going to go through faster because they're lighter, and they don't have attraction to the column, and others will go through slower, and that's how you separate them out. But you can also identify them doing this, and you can also tell how much of it, percentage-wise, was in that sample. And that'll be illustrated in this next one as well. Okay. This was a better one.
Gas chromatography, GC, is a method of separating mixtures and is particularly suited to mixtures of fairly volatile liquids. As in all chromatographic methods, there is a mobile phase, in this case a gas, that carries the components of the mixture over a stationary phase. In this case, the stationary phase is a tube called a column, packed with solid or coated with a high boiling point liquid. The components of the mixture leave the column in order of volatility, the most volatile first.
I was surprised. Some people didn't know what the word volatile means. Let me kind of show you here. This bottom axis, this x-axis down here, that's time. That's how long it takes for the stuff to get through. So this stuff came out, whatever this peak is, came out very quickly. It must have been the lightest fraction, the part that vaporizes the easiest and it's lightest. That's what volatile means. Something that easily vaporizes, that's a very low boiling point, it's a very light fraction. Okay, the other part must have been a little heavier. Also, notice the size of the peaks.
Very large.
What does it mean? The size of the peak, if you get the area under the curve, which you probably could do from calculus, right? You can tell the percentage of each of those guys in that mixture. So obviously, which of these has, which is there more of? It's the bigger peak, right? Okay. All right.
With solid or coated with a high boiling point liquid. The components of the mixture leave the column in order of volatility, the most volatile first. This is the complete instrument, with the computer control system on the right. The sample is injected here. From this injection port, the sample passes into the column, which is kept in a temperature-controlled oven.
See the column? That's that coil.
Columns are normally wound into a spiral to save space. This capillary column is 30 meters long. This is much shorter, about 1 meter. The properties of the column and its filling are chosen for the particular separation that is to be carried out. The components of the mixture are carried through the column by a stream of inert helium gas, the mobile phase. The more volatile the component, and the less it interacts with the stationary phase, the faster it travels through the column. At the other end of the column is a detector that detects each component of the mixture as it comes out of the column and also measures its amount. This instrument has a flame ionization detector which consists of a hydrogen flame burning in air. As a substance leaves the column, it burns in this flame, producing ions, which can be detected by measuring the electrical conductivity of the flame. The hydrogen for the flame comes from this cylinder here. Before beginning a separation, the operator must set the flow rate of the gases and the temperature of the oven. The temperature of the inlet port is also set at a level that ensures that the sample is fully vaporized, and the flame ionization detector must be lit. Here, we will separate a mixture of methanol and methylbenzene.
Methylbenzene. Now she has a British accent. What is that? What do you think she means?
Methylbenzene.
Methylbenzene, which is another name for
Toluene.
toluene. Take a look at the jar. Look what it says. It's a mixture. All right, what she has in there is a mixture. It's very much, as you saw from the thing yesterday you were doing, with the separation. A lot of chemistry is just separating things out. You made something, but now it's mixed with a bunch of stuff. Remember the synthesis problems? You'd often have two products. You got to separate the stuff out. Sometimes it's just a matter of boiling it off. Sometimes it's a matter of filtration. And sometimes there's other ways to separate them. Now, look at this mixture she has here. Look at the bottle. See what it says on it? Methanol and toluene.
About 0.1 microliters is taken up in a hypodermic syringe.
Look how thin the syringe is. It's tiny. 0.1 microliter.
It is then injected
Very
into the
small.
inlet port through a self-sealing rubber disc called a septum. The first peak is methanol, the more volatile component. Its retention time, that is the time taken for it to pass through the column, is about 1 minute. The second peak, with a retention time of about 1.5 minutes, is the less volatile methylbenzene.
And you'd expect that because
This
methanol's
peak
small,
has a larger area,
lighter,
showing that there is more of it in the mixture.
but there's also more of it. You can see it by the size of the peak.
The computer calculates accurate retention times and peak areas. The area under each peak is proportional to the amount of each
See how she
component.
draws methylbenzene?
The computer
Toluene?
calculates this.
Same as we would have.
This
Yeah,
instrument is used
CH308.
for undergraduate practical sessions, and samples are run singly as and when each student is ready. In this alternative instrument, the gas chromatograph is on the left, and the detector is a mass spectrometer, which runs the mass spectrum of each component as it comes out of the column.
So not only
This
can
can be
it
particularly useful when
back to that one for a
analysing an
second.
unknown mixture, as the mass spectrum can help to identify each component.
Okay, watch this.
In this
figure.
alternative instrument, the gas
This guy here to the right of him, right here, he is a mass spec. Basically, he can identify what it is based on its composition, what it's made of. So a lot of this that we used to do as, well, we've done in Chem 1, even in Chem 2, it's done mechanically now. It's done by instrumentation. For example, you notice how it burned the sample. It said it burned the sample. And that previous one had a little flame there. We did flame tests, and we were able to identify things based on the flame test. What color was the flame? Remember, back in Chem 1. But now, nobody really does flame tests like that in a lab anymore. They're done by instruments. Most of these things are done by instruments. Okay, obviously the chromatography we're going to do tomorrow, the 2 labs, you would not do this kind of chromatography for the most part. It would be done by instrument. Come on. Come on. Seriously?
Oh, that's amazing.
chromatograph is on the left, and the detector is a mass spectrometer, which runs the mass spectrum of each component as it comes out of the column. This can be particularly useful when analysing an unknown mixture, as the mass spectrum can help to identify each component. The combined technique is called gas chromatography mass spectrometry, GCMS. This GCMS instrument has an auto-changer for the samples. Many samples can be loaded up and run automatically, perhaps overnight.
Okay, now turn that light on. So, by the way, I also made this point to you, especially tomorrow. I'll make it now today because we won't have as much time. We have all that you have to do tomorrow. You know, a lot of chemistry, a lot of science, when you get to the actual industry or medical area, you're working in a lab or whatever, is just basically repetition, rote, and kind of boring. All right, if I have to run 20 samples, and it takes minutes for each one to run through, and I've got to, well, I can load the samples up, like I said, it has a thing that, but I have to be, one of the things I've always been very hard on you about is taking your observations down, writing stuff down, keep being organized, and reading and following instructions. If I'm doing a set of samples like that, and I don't label every one of them perfectly, Remember? And it's going to run overnight, that stuff. And I'm going to come in the next morning and read these. If I didn't label them, if I'm not organized, and that's like the biggest thing. I mean, I could teach somebody how to use it. You just learned how to use it right now. I mean, you could probably teach somebody how to use this machine in a day. Why do I have to have a degree to use it? I could probably teach you how to use it in a day. Well, that degree isn't so much to learn the ins and outs of chromatography as it is to learn that we hired you because you've already proven that you're not going to mess up. That's what college is about. You go to 4 years of undergraduate school as a pre-med, and if somebody dropped down on the sidewalk with a heart attack, you'd have absolutely no idea what to do. You know, you couldn't perform an appendectomy, you couldn't perform a tracheotomy, you'd have no idea. 4 years you'd have wasted because you'd have absolutely no knowledge of medicine. So why is it so hard to get into med school? They want to see who are the people who can put up with that, who can be meticulous, who can, you know, do all that nonsense and get through it. Now we know we could train that guy. It's really all about that. Anybody that tells you anything different is lying. I try to give you real world scenarios with most of the stuff I'm teaching you. Okay, even if I can't do it as part of the actual, which I usually do it part of the actual notes. At the end of every unit, we do something on, you know, something in society or whatever. But that they don't care about that in college. They're going to care about one thing: how meticulous you are in lab. Can you get through that? Prove to them that you have what it takes to go there, so that you're not going to kill somebody. Because if I run this test, whatever that test might be, or if I'm counting out pills or making up as a pharmacist, and I do it wrong, and I give a 2-year-old baby the prescription that's 10 times greater than it should have been for a 20-year-old man, it's going to kill that person. And so they want to just make sure that you're not an idiot. That's what 4 years of college is about. It really is. You will not come out after 4 years of college with knowledge of doing anything. You'll go to your job, and they'll teach you what to do, with a few exceptions. Mine will be one. Like, obviously, I learned chemistry in college. Now I'm teaching you virtually the same class. So at least those chem classes in college were exactly what I'm going to use again. But that's almost not the case in any other profession. Very few, except for teaching. There's almost no other profession that's the case. Wherever company hires you, or whatever, you know, hospital hires you as a doctor or a nurse, is going to tell you what you really need to know. Okay? Anyway, let's go over gas chromatography.
That's not bad people anymore.
Gas chromatography, as it just showed you, the stationary phase is a column. It's a wire or a hollow column packed with either an inert solid or a liquid lining the capillary column. Okay? Usually it's a solid. I think the biggest example of that is in business. You go 4 years of college in business, and you come out, and again, you just learn what you really needed on the job. You know, like my brother has a degree in business, but he got a job at a pharmaceutical company, so he had to learn all about pharmaceuticals. They didn't teach him a thing about that in college. Okay, so he had to learn it all on the job, and they train you for months at a time. The same thing's true for almost every field you go into, with the exception probably of teaching, where you actually are going to teach the same exact stuff you were learning in college, pretty much. And of course, that doesn't include professions like if I go into nursing school. Obviously, I come out a nurse. Those 4 years or however many years I was in nursing school actually were practical. They didn't just teach you, history and English and all their philosophy and other stuff. All right. So the stationary phase is a column. The liquid, the mobile phase is a gas, an inert gas. Why an inert gas? Why not just use Why not use oxygen to push it through? What will the oxygen? What might a non-inert gas do? React with the stuff inside your thing and ruin everything. Create new substances. It will create new things that you shouldn't have had there. You're trying to separate something, not make something. All right. So the mobile phase is usually helium, and that tank, that cylinder you saw to the side. You'll see those in. Matter of fact, who went down to that thing with us? Somebody in the air class said they had one of these machines was in that room. They had a peak. Remember the chart he showed you of there was like a peaks and valleys on the chart? Same thing. That was what they were showing you. They had a gas chromatogram. The sample's vaporized when you push it in there with a syringe, and then it's pushed through the column with the gas. Usually, like I said, helium. At the other end of the machine is a detector. I mean, here's all the parts right here. Here's your gas cylinder. Here's where you inject it. An oven heats it. Pushes it through the column. At the other end, you get a readout. a peak. Okay, a detector analyzes it. Depending on what that detector is, there's a lot of different kinds of detectors. It could just measure, how much of something you have and when it comes out, or it can be a mass spectrometer, in which case it can tell you pretty much the makeup of that thing. It can actually identify it. So if I asked you to read one of these graphs, I bet you could do it now. Okay, let me show it to you. You have a graph at the bottom there, right? Take a look at this graph. Is it the same one you have?
Yeah.
Okay. If I asked you, and I gave you this as a test, and I will, who was the lightest or the most volatile component? Hydrogen. And that makes complete sense because he is, from the periodic table, the lightest as well. He'll go through the fastest. He came out in 2 minutes. Oxygen, nitrogen, all these other. Who is the largest amount? How much of the percentage of mixtures you had there? What was the highest?
Carbon
Dioxide. Okay, so you can always tell from this chart that the time is always going to be on the x-axis, and the y-axis will always be the relative abundance. In other words, I could tell how much of that sample was carbon dioxide versus methane versus carbon monoxide. And it does not have to be like this, where the largest peak is always last, okay, by any means. Sometimes you get that impression, okay? Now, tomorrow we are going to do column chromatography, but I'll save that till tomorrow because that will be fresh in your mind, okay?